Okay, so today we have Nora Newcombe from Temple University in the Department of Psychology. Very excited to hear her talk about theories of spatial navigation and perception. Nora.
Okay, hi. So I titled my talk Cognitive Maps. Some people make them, some people struggle, which is similar to some titles that we've used for papers in the past couple of years. The basic idea here is that there's been a lot of discussion about cognitive maps and lately about the inner GPS that helps the brain navigate. In fact, the cells, such as place cells and grid cells, were the reason that Edward and Britt Moser and John O'Keefe got the Nobel Prize. But this makes it sound as if everybody, and rodents too, are running around with a very accurate, excellent cognitive map finding their way. But we all know, you know, this guy looking at a map tells us that it isn't always so easy. So this talk is basically about individual differences. It's also about child development. It's also about gender. It's also about the use of maps in scientific thinking. But before I get started, I want to distinguish among, or really between, two different types of spatial skills, the intrinsic and the extrinsic. So often people use the term spatial skill or spatial, even in my view worse, spatial skill in the singular or spatial ability in the singular, and they really fail to distinguish between navigation and navigationally relevant thinking and other kinds of spatial thinking. So what we're calling intrinsic skills are kinds of cognition that are centered on encoding an object, such as the shape of a pear, and then thinking about how that could be transformed, such as when you cut it in half. And the classic test of the dynamic spatial intrinsic skill is actually not cross-sectioning, although I think that's a super interesting skill, but mental rotation, which is shown in the lower left, in which people are asked to decide whether or not those block structures are the same or different, whether they can be rotated into congruency with each other. And then there are other psychological tests that maybe look at your ability to encode a structure, such as the embedded figures test shown in the upper left. But those, while very interesting, are quite different from encoding an environment. An object is something that you hold, and an environment is something that you walk through. And when you're encoding the relation of the various bits of an environment, the mountains, the roads, the church, etc., to each other, that's a different kind of encoding, and then also a different kind of transformation as you try to work out where something would be, how it would look if you move to a different perspective. So there are other tests of the ability to take perspective, two of which I've shown at the right. And in fact, quite a lot of research over the past few decades has shown us that mental rotation and perspective taking are distinct, which is really interesting because they're computationally equivalent. You could write a computer program that would just turn one into another, but they've been shown to be behaviorally dissociable for quite a while, and I won't go into that research. And they also seem to engage different neural substrates. So in particular, this perspective taking, imagining a layout of the church, the roads, the mountains from a different perspective, engages navigationally relevant parts of the brain, such as the retrosplenial complex and the hippocampus or the hippocampal formation. So I think that's important to bear in mind as you read the literature. Now, when we are thinking about navigation, and there's a recent book just out which gives us a nice overview of a lot of aspects of human spatial navigation that I highlight here, but I would say that the modern synthesis is the idea that there are two systems that combine to support spatial memory for an environment and finding your way. One of which is dead reckoning, which is the body-based system that I guess you've heard about in some past lectures, how far you've moved and whether you've turned or not, and then the combination of those rotations and translations. And then also what we call allocentric frameworks, such as where you are in relation to preferably visible non-moving landmarks, such as mountains. But there's all these tales of exploits, such as the South Sea Islanders sailing from island to island using these two systems. So still, it's sort of sounding like building a cognitive map is not that hard. These South Sea Islanders do great. They combine these two systems all as well. But we know that building a cognitive map can be challenging. And here's an example from a map of the area that I grew up in, which is in Ontario. And I actually grew up at the western tip of Lake Ontario. You can just see Dundas highlighted there. It's a kind of suburb of Hamilton. But what you can see is that there's a bunch of roads that would be going east from Dundas to go into Hamilton. And then there's other roads that would be going east, but along the north shore of Lake Ontario that would actually take you into Toronto. So you're in this funny position of taking a road marked east to go to Toronto, a road marked east to go to Hamilton, but Hamilton is not between Dundas and Toronto. The reason being that there are angles involved that a lot of people would have failed to encode. And I actually grew up failing to encode these and being more or less permanently perplexed about where everything is. So these are the kinds of things that we think of when we think of individual differences. And in fact, there's, despite the fact that cognitive map is a classic term in psychology, and Edward Tolman used it at the turn of the last century, and O'Keefe and Nadell used it when they talked about the hippocampus as cognitive map. Many people, both a long time ago and much more recently, have been talking about the ways in which we seem confused. We think that A is closer to B than B is to A. And most recently, Bill Warren at Brown has been conducting several experiments that he suggests shows that people don't think very coherently about cognitive maps at all, that they happily go through wormholes and never really realize what's happened. They just go ahead trying to think where things are. Now, I actually have quite a lot of criticisms of Bill's experiments, which we won't go into today. But one of the kinds of answers that I would offer to the challenge that Bill offers the cognitive map idea is that it might be that some people form cognitive maps and some people basically don't, or form very imperfect ones. And this was an idea that was actually, it's been around for a while, but there's an experiment by Teru Ishikawa and Dan Montello that appeared in 2006 that really support that, in which they drove UC Santa Barbara students around in the hills above Santa Barbara, and they took either an S-shaped route that you can see at the bottom of the map, or a U-shaped route that you can see at the top of the map, and then later they were taken on the other route, the one they hadn't taken, and then they were taken on a connecting route that you can sort of see in the middle, and then they were probed at various junctures about their sort of conception of the environment. And I'm not going to show you the findings. Basically, they support the idea that some people are good. They actually figure out how the routes are related even before they go on the connecting route. Some people ultimately learn, and some people remain permanently confused. So we did a very similar experiment. In fact, it used a U-shaped route there in blue at the bottom, and another kind of U-shaped route shown at the top in gold, and then two connecting routes shown in green and in red. We used two connecting routes because we thought that pinned down the relation between the two separate routes better. That didn't turn out to make too much of a difference, though. We also used a walking environment because we thought that being driven around didn't really give people much of a chance to really put things together. And again, I'm not going to show you too much data because what we found was a lot of individual differences. But we were only able to test a relatively small number of people because it's hard, as probably you know, to test people in the real world. It rains, it doesn't rain, etc. And you can't control cues that some people may use, such as the sun or the absence of the sun on cloudy days. So we did go ahead and make what we called initially virtual Ambler, and now we've been calling Silcton, which is just a desktop program. But we've had a lot of success with it. It's actually modeled on the Ambler campus, so it's more or less this kind of layout. But these buildings are much nicer and grander than the Ambler campus. And what people do is to follow this route shown in red to stop at various marked buildings, such as Snow Church. There's a diamond there that tells them to stop and to remember where this building is. And they can't leave the road, although you can make a free exploration version of the environment. But we set it up so they couldn't leave the road, but they could at any time turn around, look wherever they wanted, retrace their steps if they wanted. So in that sense, it's free exploration. So they explore the environment one route at a time, just like Ishikawa and Montello. Then they experience the connecting routes. This is the map, which they never see. And then they are tested either by pointing from one building to another. This is in situ pointing. So you are where you are, you're in the virtual environment, and you're told to point to Harvey House using this kind of rifle sight, and we record where you point. And those directions are either on the same route that you're on right now or on the other route where you've experienced it separately, but then perhaps link them by the connecting route. And the other thing we had people do is a drag and drop model building task. So they saw overhead views of the various buildings. They saw a view from the familiar view of Snow Church, which alerted them as to what it was that they were being asked to drag and drop. So they didn't really have to interpret the overhead views. And they could rearrange what they were building until they were satisfied with it, at which point we scored it using bidimensional regression and got an overall accuracy score for the model that they built. So the basic findings, which have shown up again and again, and I'll show you several of these graphs, involve the way people handle the within route pointing, the between route pointing, and the relation between them. So there's a group of people that we call integrators who are pretty good at the within route. They're, between some of them are as little as 5 degrees of error, and some of them range up towards 20. And on between route, they tend to be a little worse, and we sort of let them go up to 40 degrees of error, but they're pretty good. Now, this is a score where 90 would be chance because it's on either side of the correct point. And you can see they're very much better than chance. There's a group we call the non-integrators who are close to being as good at the within route pointing. They've learned the routes as the integrators, but they are quite a lot worse at the between route points. They're not a chance, albeit the guy or girl who's out by 75 or so degrees is getting a little close to it, but they have a large amount of error. And then we have this group we're calling the imprecise, who really have quite a lot of error on both. They know the routes a little better than they know the relation between the routes, but they have quite a lot of error on both of those. Now, one thing you may be thinking about is, well, even the person in the lower left who's at 5 degrees on within routes and maybe 12 degrees on between routes, is that good enough? It's not perfect. And let me just remind you that this is, pretty good, and definitely good enough, I think, to navigate. In fact, navigation instruments will often only resolve your position within 15 to 20 degrees, and using that you can go ahead and sail down the middle of this cone of uncertainty and usually correct the route from another fix on a landmark. So we've looked at individual differences. The Santa Barbara Sense of Direction Scale, which is a self-report measure. In this particular study, the integrators did say they were better, so they know they're better. The non-integrators didn't particularly differ from the imprecise navigators, so they didn't realize that they at least knew something. They knew the routes. And alternatively put, the imprecise navigators didn't quite realize how bad they were. Now, they also, looking at the right, the PSAS is a measure of those small scale skills like mental rotation. They also say they're a bit better at that, but you can see it's dampened. And nobody says they're any more verbally able than anybody else. So that is, we're not just looking at boastfulness about your navigation ability or anything like that. You can also see that the integrators do better both on PTT, perspective taking, and on mental rotation. But I'll say more about that in a minute. So we found this again and again, as I said. And we also had a go at looking at the question of whether or not people who are good, the integrators, remember the routes and then link the routes, or whether they just mush it all together. They have an overall cognitive map, forget the routes, they know where everything is. So we gave them a task in which they had to decide if two familiar buildings, so they've seen both of these buildings, are they on the same or different route, as fast and as accurately as they could. And what we find is that the integrators do better than the imprecise navigators, and the non-integrators also do better than the imprecise navigators. And the non-integrators and integrators are not significantly different from each other, although you can see they're ordered as they sort of ought to be. So when you get good, you don't get good by mushing everything together. You do remember the routes separately. In fact, you do that better, as perhaps the pointing errors already told us, than the people who don't do as well. So we've used this tool in a whole variety of situations, not all of which I'm going to take the time to tell you about. But one of them, since I am originally a cognitive development person, that I was eager to do was to study development. So we published a paper on children from 8 to 16 years of age. Their average age was 12. And we gave them the basic Silcton task and mental rotation and perspective taking tasks. And what we found was that there is development, and it's a little faster for the within route in black than it is for the between route in red. The children reached, well, this is cross-sectional, but the age at which you see adult levels of performance is about the age of 12. The 8-year-olds are not bad. You may wonder, given that, why we didn't test 6- and 7-year-olds, and the answer is that they, won't sit still for this long a procedure. So we don't quite know where they might emerge from chance performance. And model building showed us the same picture. About the age of 12, children did as well as adults do, overall as a group. They also showed the same typology that you've seen before, with the 8 to 10-year-olds more likely to be imprecise, the 13 to 16-year-olds more likely to be the integrators, and what I hasten to add is there certainly are some precocious integrators, there's some elderly imprecise people. We've just recently completed getting back about half this sample about 2 years later, so we'll know something soon about longitudinal profiles and stability. But certainly the distribution already looks adult-like, as well as the mean levels. Since we had mental rotation and perspective taking, we were able to look at which was more important. And I already gave you some reasons to think that perspective taking would be more important. And indeed, that was the case looking at development. Perspective taking accounted for more of the age variance. And just in general, it was significant on more of the analyses, and also specifically quantitatively accounted for a higher percent of the variance than mental rotation. So that's some reason to, again, zero in on perspective taking, which is a very well studied topic in cognitive development. But Andrea Frick and I have turned it into a test that you can give to kids without too much ado. I'm very into making these tests portable and ones that are open access and that can be used across labs. And what you can see is that there's a big improvement between 7 and 8 years of age, which is more or less what Piaget found. There are ways to make this easier for kids as young as 4 and 5, but when you do the test the way Piaget did it, the improvement is late. So it may be that the reason the 6 and 7-year-olds didn't want to do Silcton is because they were so bad at it that they didn't want to do it. And it's only the 8-year-olds who were really able to do it. It's just always very hard to tell when kids won't participate. Now, this is a point that I want to make that is germane to what we're talking about with respect to VR. It's a study of adults. So we're back to adults briefly. With a dollhouse-sized display divided into 4 rooms that people can either rotate on a lazy Susan, so that's then rotation, or they can walk around it. And they can also be pushed around it, or they can watch the array being rotated, or they can just see successive static views of each of the 4 rooms. And what you can see here in the graph in respect to global judgments is really pretty simple. The people who see static views or watch the array rotate or even rotate it themselves are doing very, very badly. The people who are pushed around it are doing maybe a bit better, but the real story is if you walk actively around it, you put together the dollhouse the best of all. Now, this does argue that not using desktop VR would be better, that we're underballing the degree to which people can succeed at these kinds of tasks by using desktop VR. But as I was also saying, in experiments where we tried to put Silcton on a Vive and use teleportation, we did not find that that improved anybody's performance. So I think if they were really walking, maybe they'd be doing better, but immersiveness is apparently not the key. So I'm just going to point you to this developmental model. This is I'm not going to describe it at all. It's really just, if you want to know more about development and not just about Silcton, I recently published a review of this literature, which I hadn't reviewed in about 20 years, so I'm kind of proud of having put it together again. I wanted to spend a little time talking about sex differences, because I bet none of you can ever give a talk like this without being asked about sex differences. And we've recently done a meta-analysis of this literature, which is currently under review. There had been some prior work. There was a literature review in 2004, but it was a narrative literature review. And there was a meta-analysis of rodent studies, which actually interestingly showed that different strains of mice and rats, some of them show sex differences and some of them don't, which will give you pause if you ever read the rodent literature and some of you, oh, those female rats don't do very well. Well, you ask what type of rat they are. So we decided to do a quantitative meta-analysis of the human literature. And John, I think you might have even sent in some data, or maybe we just found some of your data. And here's what we found under review. So are there sex differences? Yes, males outperformed females. But what is the magnitude? This effect size of whether it's 0.34 or 0.38 depends a little bit on what you include and how you calculate it. But this is a small to maybe sort of moderate, but very much at the small side of moderate sex difference. And interestingly, it's much, much smaller than the sex difference that is shown in mental rotation, which I've been emphasizing is a very different spatial skill. I would argue from an entirely different sort of bit of human cognition, because those sex differences are more 3/4 or even close to a whole standard deviation. So these are much smaller. We also took a lot of looks at how task variation moderated this sex difference, and we did find some significant effects, but I don't want to go into them because I'm not sure that all of them are really there. Some of them are anchored by just very, very few studies. And the important point is that you never get to a whopping big sex difference, nor mostly do you get rid of the sex difference. The one way that you really create a fairly big difference is if you divvy up the sample by age. And what this graph is showing you is that the light blue in the top left, which is for studies that have looked at children less than 13 years. So these are children before they've reached these adult levels that I was emphasizing to you at the age of 12, are showing very small sort of 0.15 type sex differences. They're still favoring males, but they're really much smaller than all the other ranges of effects. So I want to close by talking about how expertise is involved and why we should care about navigation other than, oh, it's interesting, and oh, you shouldn't get lost, and those kinds of considerations. But navigation, and it's intimately related to maps. And now I'm talking about cartographic maps, not just cognitive maps. And the classic example of the use of maps in science is the middle panel, John Snow, not that John Snow that some of you might have seen on TV last night. This is Sir John Snow in London discovering the causes of the water-based transmission of cholera by looking at where the cases are in relation to the water pumps. But there's many examples, epidemiological on the right, how the HIV virus traveled out of Africa. Crime maps, looking at Hamilton, Ontario, back to my hometown. This tells you the area that you don't want to be in at night. So these are the kinds of distributions that geographers and other kinds of spatial thinkers use. And interestingly, when you look at scientific disciplines, what you see is that in the upper left on the Santa Barbara sense of direction scale, people who do geoscience or geography, those red bars sticking out to the right, tell you that they self-rate as very high on navigational thinking. Interestingly, engineers and physical scientists do too, except biological scientists don't much. And then in terms of other kinds of self-reports, basically there's quite a lot going on with the small scale spatial skills. The geoscientists, geographers also self-report being good at those. That's the middle panel, but there the engineers are also sticking out. This is more the mental rotation. But when it comes to verbal skills in the top right, it looks different. The engineers aren't claiming to be good at verbal skills. So are geologists better at Silcton? This is self-report. So we wanted to move to an objective assessment, and we gave Silcton to both PhD or master's level geologists and PhD or master's level psychologists. And it's sort of superimposed on a gray background of all our various undergraduate data. And what you can see is that the geologists in the black squares are much more likely to be down there in the lower left. They look much more like integrators. And my psychology colleagues, some of them indeed are integrators, but they also go much more to the right and then even to the upper right, which isn't, you know, there are two geologists up there in the upper right. Discipline is not destiny, but there definitely is an expertise-based objective difference in navigation skills. So that brings up the eternal question of whether this is self-selection. People who are good at navigation are attracted to these kinds of disciplines, and people who are not so good go into psychology. Or whether there's something about working with this kind of material that enhances your navigation skill. That is there malleability in navigation skill? And we think there is a little bit of both. This is based on a study. Actually, it says under review, but yesterday it was accepted. I'm proud to say that it will appear in Cognitive Research Principles and Implications. And what this shows you is that on Silcton, our tool of interest, the GIS in red show lower error, both before they start the GIS course, so they're self-selecting, but they also decrease their amount of error. They're going down over the course of the semester. By the end of the semester, they show less error, whereas the communication students really don't change. And we see the same pattern on model building at the right. Here up is good, so you see both self-selection, but then the red GIS students get better and the communication students just stay the same. Now, they do also, the GIS students get better at mental rotation. I don't know why we didn't give perspective taking. I'm a little irked about that, but we're correcting that in an ongoing study. But we do see some evidence of self-selection and of differential improvement, which raises the question, perhaps, of are GIS classes just great for your brain in general and not so much communications classes? But what we see on a working memory test is that actually both groups go up in parallel, which may be just a practice effect. We also, by the way, see that the communication students aren't as good at working memory, which does cast a little bit of doubt on perhaps the self-selection effects. Maybe smarter people in general are going into GIS courses. What I think the data, however, can't be explained that way for the interactions. So one way of improving your navigation skills is to take a GIS class. That maybe isn't the easiest thing to do. It's a semester of strenuous cognitive effort, but it certainly leads us to think that navigational thinking is malleable. And note that GIS classes are not all about navigation. Quite a lot is about coding, interestingly, but you're always thinking about map-like distributions. So that's it. I think I've left plenty of time for questions and discussion if you're interested.
I imagine John does too. And of course, we have people watching online. If you want to pose any questions in the Q&A or the chat, then we can find them there. John, you want to go first? Be loud.
Sure. Do you want me to use this?
Sure.
I will leave these accessible, but for now I'm going to take the slides down because I think that'll help me to see more.
Lip reading. Okay, good. Thank you, Nora. I really enjoyed your talk, and I love hearing about your work. And there were some, despite the fact that I follow your work closely, I still learned a lot of things that you're doing.
Oh, thank you.
So I appreciate that. I'm interested to know. So, as you know, Stephen and I are working on this project where we're talking about the importance of self-motion cues to processing space, and your virtual Silcton, they're navigating in desktop VR, and I wondered what you think would be the outcome of adding in additional self-motion cues like walking or turning the body, and whether or not individuals might move around from one category to another in terms of whether they're integrators or imprecise navigators and so on.
Right. That's what I would like to know too. Absolutely. And the study that I mentioned doesn't answer it because there were different people in the Vive version versus the desktop version. So The one thing I will say is that if people move around, some would have to get better and some would have to get worse to give you more or less the same distribution. So I sort of suspect that isn't true, but we don't really know.
Yeah, that makes sense, and I agree. Looking at your figures from the two different studies, it seems like those groups of people exist no matter how you have them interact with the environment. So those realistically could be the same people, and if you were to test the same people, they might stay in the same category.
But note that the Vibe version is the version where you teleport. So what I think we don't know, and maybe you guys will find out, is whether or not people overall are better when they can really move, and whether the distribution, in fact, might change. Maybe some people more than others really need to really move. And also, what's key, as you know, is avoiding cyber sickness. But I just want to point out, that's really key, because if you discard like 40% of your sample, excuse me, who are you discarding?
Right. Absolutely.
Are they the good ones? Are they the bad ones? Are the people who more need those cues? Who are they?
So one of the things I'm always interested in as a parent of a young child is developing his spatial skills.
Sorry, what's that? Yeah. Yeah, go ahead.
And one thing I noticed that my son, he's 5 years old, and he really likes doing Legos and sort of the object-based things like you described, sort of that I think in my mind seem to fit sort of a mental rotation approach to solving problems, of looking at instructions and then creating an object that looks like it. And then I think he's getting quite good at that, and I think part of it's through the experience. On the other hand, I ask him to do things like, point to this restaurant where we like to walk to. And basically what he does is he points to the street that we walk down to get there, even though that may not be the correct direction. So it feels like he's very far away from having a cognitive map. Now he's only 5, and I enjoyed seeing your slides of how those skills develop over time. And but I also wondered, in the spirit of thinking about how to develop skills and how they're trained, how is it that skills like perspective taking develop? What are the activities that we engage in that develop perspective taking per se, as opposed to mental rotation?
Right. So, yeah, pointing in the direction from whence you came is something that John Reiser actually found kids doing back in the day. I've always been a little worried that it depends on how kids understand the question, because on some level that is how to get there. So understanding that there would be an alternative way or a shortcut. I mean, even if you can't take the shortcut because it would be through a building or whatever, but sometimes you could take the shortcut. So that's where I think we begin to get some idea of what the experiences might be that would build this capability, that you would start showing children that you can take a shortcut. You would start explaining to them what you even mean by the question of where is it. You would start using maps. David Utah has done plenty of research to suggest that children as young as 5 or 6 can understand maps. Maybe not perfectly, and of course Lynn Libben has some data to show that they have certain misconceptions and errors, but there are actually kindergarten curricula that work on building up little kids' ideas of maps. And Lynn Libben and Kim Castens came up with a curriculum for 4th graders that works on maps. So, you know, people have been thinking about this problem, and I think that it's basically, you know, it's an undervalued skill in our society, and you can, I think, fairly easily think of ways to develop it better.
Yeah, that relates to my question. I wondered if any of this, if you have any sense if it's trainable, a nature versus nurture situation. Either the sex differences or any trainable, you know, are the men trainable, are the women trainable on that, or the kids trainable, or on the, do you have any sense if this is nature nurture?
Right. Well, this is a pretty big topic. With respect to navigation, I think we don't at all know the answer because there's been so little study of training efforts and malleability, and especially that would be designed to answer the questions you pose. But in the meta-analysis that David Utah and I did of the small-scale spatial skills like mental rotation, which actually included the paper and pencil tests of perspective taking, which arguably do relate better to large-scale navigation. What we find is evidence for considerable malleability. Now that's a moderate effect size. That's about 0.5. I don't want to overstate it. It's also, however, relative to the training techniques. You don't know if you did more training, better training, whatever, maybe you could get a larger effect size. But in the studies that have been done, those effect sizes are pretty constant over the different types of skills. So they're there at that size for both mental rotation, perspective taking, embedded figures tasks, horizontality, verticality, and one other that I can't remember. They're as present for little kids as for adults. So, which is funny because developmentalists often think, oh, you're more malleable when you're a little kid. If you're going to improve, let's do it early. There was a hint of that in the meta-analysis, but it did not in the end come out significant. I still vaguely suspect it might be there, but if it is there, it's not a big deal. So the good news, though, it's bad news for developmentalists who like to think kids are malleable. It's good news for adults. That means they can really improve. There's no excuse for saying, I'm just bad. No, well, you're bad. Just pull up your socks. Anyway, in terms of gender, both men and women go up. They go up in parallel, so you don't get rid of the sex difference with training. Now, that, I think, speaks to how culturally undervalued these skills are, because even men who are good are not as good as they could be, not by a long shot. So I think what we don't know the answer to is if everybody improved to the sort of limits of their reaction range, are the male and female reaction range is actually the same. I think we just don't know the answer to that.
It is nice evidence, though, that they are trainable to some extent.
Yeah, and I've always argued that from the sort of social usefulness, social policy perspective, what's more important than the nature-nurture question is how malleable they are. So even if men and women have different reaction ranges, if they're so both underballing their reaction range, the more important thing is to get everybody closer to the top of the reaction range.
Here's a different question. On your graphs where you plot the 3 types of people, how do you find your dividing lines? Because some of the points look really close. I didn't know if it's just a mean or how do you do the slicing?
Yeah, we use various statistical clustering techniques to get to that. And we've also looked into whether you're just fairly arbitrarily cutting a continuous dimension or whether there's evidence for sort of an underlying class there. That's a little equivocal, that test. It's not clear that it is a class. It's not clear that it's not a class. So right now I would say that we present it that way partly because it just looks better. It's easier to talk about, that kind of a thing. But it's using statistical clustering techniques.
Okay. Can I do one more?
Yeah, please.
So I have a different study going where we're looking at the read the mind and the eyes test. Do you know about this test where you...
Oh, I do, yeah.
The photos of the eyes and how the extent to which people can read these emotions on expressions.
Simon Baron-Cohen.
Right. Have you by chance run across any correlation between that sort of ability and navigation or perspective taking? I was just curious because you would be the one who would know.
I have a graduate student who's actually developing a proposal along these lines, so I would love to know what you're doing. She's been reviewing the literature, and I think, I'd have to double check with her, but I don't think she's found a study that does that. I don't really love that test, though. I don't know. I think if we're going, with Maria, we are currently selecting our tasks, and we're actually thinking that we won't use that task. We want to use some referential communication tasks because they seem to be both spatial and social, but then to use some straight up emotional perspective taking that does not involve spatial thinking. And I agree, reading the eyes test sounds like it would be that. We just sort of don't like it that much.
Yeah, our study was, can you be trained to do it better? And so, so we had three different modes that people went through. Three different kinds of, I guess, a control condition and two kinds of training. One of the kinds of training was sort of strategic, like let me tell you how to look at a face, this sort of thing. And the other was just practice, like take the test 5 times. But in the strategic one, though, we ended up developing sort of alternative questions based on Pixar animated characters because they're so evocative with emotion. And so they were a lot clearer than a lot of the British words used with the original test and the black and white pictures. But it's in preparation. We're about to submit it. So, but I'd be happy to talk with the student or you.
Great, yeah. Or, if you're ready to share it, I'd love to see it. Yeah. Great.
On your landmark thing with comparing the two buildings, did you find that it was useful or needed to somehow rate the saliency or the memorability of these buildings?
Well, we didn't do that. There actually aren't so many buildings in Silcton. We have evaluated their memory for the buildings separately, and also their memory for the names of the buildings. People do pretty well on this. There's some suggestion that a little bit of the problem of the non-integrators may be that they don't do the brute force memory, like which one was Snow Church anyway, the sort of paired associate learning quite as well, but they do pretty well. And in Corinne Holmes' work with the dollhouse, they do great on just, picking the pieces of furniture out of a lineup and, this kind of thing. So I don't think those aspects of the tasks are that important.
Okay. My last thought was that a couple of weeks ago, I was at the Cal Berkeley Center for Extended Reality giving a talk there. And I had never been to Berkeley before, and I had looked at the map, and I thought, oh, there's my building, and the map has nothing about the fact that it's on a gigantic hill. Right. So I mean, the whole campus is built on the side of a hill, and it's very steep. So it made me wonder if any of these studies are looking in that third dimension of hill, because I can imagine my salience of direction. I may not know which direction that building in, but I know it's up.
Yeah, no, Steve Weisberg and I have looked into that, and I also have some studies with Danielle Nardi on this topic. I think slope is a really neglected cue and a really important one. Berkeley is the example I actually always use, because if it's down, it's west. If you're looking down, you could see the bay. There might be something in the way, but just get that thing out of the way, you will see water. And I don't understand why people don't use that, but often people don't. It really is quite perplexing. Now, Berkeley it's easier to use because that's pretty much true everywhere. There are other environments where, like actually a part of Philadelphia called Manayunk, where you go up and then you go down. It's sort of not quite as clear. But it's still a pretty good cue if you just get the topography right. And one of Steve's findings, which was also in VR, and it was a different environment. It wasn't Silcton, and it wasn't the best VR. This was back when he wasn't so good at Unity or whatever. But it did seem that there were people that, if you're good at getting the configuration of places on the flat, that's when you can cope more with slope. So it's interesting because again, the rich are getting richer. The people who could do it anyway are the people who can then exploit that additional cue.
Yeah. Well, this has been a wonderful talk, and I think we're about out of time.
Okay,
Thank
well,
you.
good. We've identified lots of interesting points of contact. We'll have to stay in touch.
Okay. Thank you.
Yeah. Okay. Bye.
Bye.
Well, thank you.